For this video, I'm going to take a look at the 2017 AP Calculus Free Response, specifically question number 4, which was the differential equation from that year. And this is non-calculator, so we'll keep that in mind as we go through. So our story, at time t equals 0, a potato is taken from a pot in a stove and left to cool. The internal temperature of the potato is 91 degrees Celsius at t equals 0, and the temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t minutes, so give some units there, can be modeled by the function h that satisfies the differential equation shown here, dh dt. So just keep in mind that means that whenever you think h is really the antiderivative of that differential equation. And it gives units for h of t, says that those will be in degrees Celsius, and it restates an initial condition from earlier, h of 0 equals 91. So in part A, we're going to write an equation for the line tangent to the graph of h at t equals 0, and then use that to approximate the temperature of that potato at time t equals 3. And so for part A, tangent line equation, we always need x, y, and slope, or in this case, going with the variables they have, our x will become t, and we're looking at t equals 0. We'll have h of 0, which we were told is 91, and then we need our differential equation evaluated at time 0 and temperature 91, which will be negative 1/4, 91 minus 27, and there's nowhere to plug a t value in, so we don't have to worry about it. This one, just because we're going to write the tangent line equation, might be a good idea to simplify down this dh dt. If you choose to leave it, just make sure you carry that expression around accurately. So I have negative 1/4, the 91 minus 27 should be 64, and that'll give us a nice negative 16. And so our tangent line, again using the variables provided to us, be h minus our y value, which was 91, equals our slope times t minus 0. And this one, since we're going to try to use this to approximate h of t, use it at time 3, I'm going to go ahead and solve this for h. The right side will simplify down to negative 16t, and we'll have plus 91. And then we'll use that to say that our temperature at time 3 is approximately negative 16 times 3 plus 91. And you can close that off with degrees Celsius and be done right there. If you choose to simplify it, so we'd have negative 48 plus 91, so you should get 43 degrees Celsius. Again, just be careful on those numerical simplifications. Don't lose easy points that way. So moving on, part B says we are going to use d squared h over dt squared, which is our second derivative, to determine whether our answer in part A is an underestimate or overestimate of the temperature of the potato at time 3. So with that, especially if you're not used to talking about over-under estimates for tangent lines, we're not maybe quite sure what this problem is asking. Think about h of t itself would be some sort of curve, and we've made a line tangent to that curve. Everywhere except for that point, the curve is going to separate itself from the line. It could look something like what I just drew, or if the curve were more like this, the tangent line and curve would separate in this way. And what's going to determine over or underestimate is concavity. Concave up, the tangent line would continue to be lower than the curve, and we would have an underestimate for concave up, and we would have an overestimate if our actual curve was concave down. And so they're kind of giving you the hint by already telling you to find the second derivative, but even if you didn't understand this part of the direction, we should all be able to find the second derivative for this equation, and then I'll show how we can answer the over or underestimate problem. So we're going to start by going back to our dh dt. And since I know I'm going to differentiate this, I'm going to go ahead and distribute on that right side. Get negative 1/4 h plus 27 over 4. And now I'll take the second derivative with respect to time. And notice the reason for doing that was it makes this derivative just look a little bit nicer. We will just get negative 1/4 dh dt. But we prefer to have any equations in terms of the variables given, so I don't really want this dh dt in there. Well, luckily, I already know what dh dt equals, so I can just substitute that into this new equation. And putting that all together, I will get a positive 1/16 times h minus 27. And now to answer the question on the over-under estimate. And if you can understand why we have to just look for concavity, all we have to do is talk about the concavity of our equation at time 0. And so looking at our second derivative, what we can actually do is we don't even have to worry about at t equals 0 because notice you have a positive 1/16. We already know h is greater than 27 throughout this entire problem. So we can kind of take a shortcut and say since h of t is greater than 27 for all t greater than 0, h of t will always be concave up because our second derivative will always be positive. And therefore, since we are concave up, we can look back to the first picture I drew. Therefore, our estimation, actually I guess I should use their terminology, therefore our approximation in part A is an underestimate. So like I said, even if you don't get that last part, if you got your second derivative equation and you correctly chose to substitute in dh dt into that equation, you're at least getting credit there. And if something like this were to pop up again, you'll be prepared for it. And so we're about halfway through our time, and parts A and B, if I hadn't been stopping for explanation on some of those, you can see that those two parts are pretty short, which should prepare you that part C is going to take a little bit more of our time. And in part C, for t less than 10, an alternate model for the internal temperature of the potato is the function g that satisfies the differential equation dg dt, and it's this negative quantity g minus 27 to the 2/3. G of t is still measured in degrees Celsius, just like h was, and g of 0 is still 91. It's the same initial condition. But what this one says is find an expression for g of t. Normally we've seen this direction as find the particular solution, but once you realize we have to get g of t from dg over dt, we have to realize we're doing the antiderivative, which means we're going to have to do our separation of variables, and that's why this part takes a little bit longer, also going to be worth a lot more points. So for myself, I'm going to go ahead and recopy down dg over dt. And in order to get the antiderivative, we're going to first separate out this notation on the left side. I always like taking this step first. Just multiply both sides by dt. And then all I want to get rid of is the part from the right side that has a function g in it, which is just that g minus 27 to the 2/3. I'll go ahead and leave the negative sign over there on the right side because it's not really hurting anything over there. So dg over g minus 27 to the 2/3 equals negative dt. And now we can go ahead and get the antiderivative of both sides. For our purposes here, I'm going to go ahead and move this up to be g minus 27 to the negative 2/3. And just noticing, I mean, it's a first degree expression being taken to a power. It's going to integrate a lot like if I had just had dg over g to the 2/3 itself. So using that negative exponent is going to be a little bit more useful. And I will keep this negative dt over here. And so the integral of the left side, I'm going to get g minus 27 to the 1/3 and with a times 3 out in front of that. And I don't need to worry about anything from this having come from chain rule. Derivative of g minus 27 is just 1, so I don't need to worry about taking care of that on the way back. No need for u substitution here. And this is going to equal negative t, and I'll include my plus c on this side. At this point, you have the option to go ahead and solve for c here. I always prefer to get my dependent variable, y, g, whatever it might be. I usually want to get that on its own first, but it's up to you. As long as you solve for c accurately at this step, you can go for it. Myself, I'm going to go ahead and get rid of the 3 from the side. So I have a negative 1/3 t plus c. Since I'm dividing c by a constant value, I don't have to worry about noting that. It's just going to make a new constant. I'm going to go ahead and cube both sides. And since this is a function operation being done on this side, the c has to be included there. And the opposite of a 1/3 power, make sure if you didn't quite see that at first, rewrite that 1/3 power in root notation just so we can see why we have to cube both sides. And finish up by saying g of t equals this negative 1/3 t plus c to the 3rd plus 27. And now we'll go ahead and solve for c, knowing that g of 0 equaled 91. So negative 1/3 times 0 plus c to the 3rd power plus 27 equals 91. So what we're going to get c cubed plus 27 is 91. C cubed in that case would equal 64, and the value for c would just be 4. And so our actual g of t equation, again, make sure you write that final equation down, whether it is your last step or even if it's not, we still want to make sure we're showing the entire particular solution to whoever's grading our paper. And then the last thing it asked us to do was to use this model now to approximate g of 3. So, negative 1/3 times 3 plus 4 to the 3rd power plus 27. And you could technically leave that and just go degrees Celsius on it. Be done right there. If you choose to keep going, we would have negative 1 plus 4 cubed plus 27, which would be 3 cubed, which is 27, plus 27. We would actually get a final value of 54 degrees Celsius. And looking back, we got our expression for g of t. We got the internal temperature at time 3, so that part is all done. And that does it for 2017 problem number 4. Good luck studying for your AP exam, and thank you for watching.